Okay, so up to this point, we have seen that the set of naturals by definition is countable, set of integers is countable, and finally we have seen set of rational numbers is countable. What about set of real numbers? Is the trend continue? Is the trend going to continue here? Is the set of real numbers also countable? Uh, let's see. Now, to do this, it's going to be a contradiction proof. So we are going to start with this assumption that set of reals is countably infinite. So this means there exists a list similar to the list of rational numbers that I have just mentioned in the previous slide. You have just a list of real numbers, the entire list, and you can start from the first one, whichever that is, according to your order, and then the second real number, the third real number. So it makes sense to make in this scenario uh, to say the first real number, the second real number, etc. So there is a list. That's essentially what countable means. You can actually list them in a rigorous way, in a systematic way. Now, we are not going to look at the all real numbers. We are just going to look at the real numbers in the interval, the open interval 0 to 1. Okay, so this includes all real numbers in the form of 0 point something. So 0 0.53725890012, etc. Okay, if it's really like so, that's also fine. Okay, so we have, let's say, the set of all the real numbers in the interval 0 to 1. Doesn't really matter which order you use, just assume there exists an order. So this could be, this one, for instance, could correspond to something like this. This could correspond to something like this. This could correspond to 0.002879052, etc., whatever. And this could be 0.9809000780, whatever. Okay, it's just a list. You have come up with a procedure to produce a list, and this is the list. And this means here every real number in this interval exists in this list. That is what it means. This set is countable means you have a procedure to define such a list, and in this list, built according to that procedure, you have each and every one of those real numbers in this interval. So none is left out. Now, consider this number 0 point d1 prime, d2 prime, d3 prime, etc., where every digit here is obtained from each of these by adding 1 and taking mod 10. Okay, so what does that mean? Add 1 and take mod 1, mod 10. It means if you just increment it, and if it was 9, make it a 0. That's simple as that. Okay, if it is 3, make it 4. If it is 6, make it 7. If it is 0, make it 1. If it is 8, make it 9. If it is 9, make it 0. That's it. It doesn't even have to be this. Just change it. That's the idea. Okay, so take the first digit from the first real number, the second digit from the second real number, the third digit from the third real number, and so on. And each of those digits that you take, modify it. And here I'm incrementing them because, well, it's easier to define in this way. Okay, so if you remember this, now what I'm going to do is I'm going to build a new number, 0 point. So this is going to become a 6 here. This is going to become a 4 here. This is going to become a 3. And number 4, this 9 is going to become a 0. And whatever the fifth number is, I'm going to take its fifth digit here, increment it by 1, put it here, and so on. okay? And this is going to go to infinity because I have infinitely many reals here, obviously, okay? Now, this number described in this way cannot be in this list. Why? Because it differs from all of these numbers on at least one digit, so it's not equal to any of those numbers, which means it is impossible for this number to be in this assumed list. We assumed that this set was countable, and this means this set should be countable. This means I should have a list to list all the reals in this interval, but I have just shown that there exists a number which cannot exist in this list defined in this way. So this is a contradiction, which means my first assumption was incorrect, right? So this proves the set of real numbers is not countable. This is called Cantor's diagonal argument because it uses, you see, diagonal digits here for the proof. And it was very important at the time, and he proved that the set of real numbers is actually bigger than the set of natural numbers in cardinality, right? The number of real numbers, well, it's not the number, but we cannot say the number because the number is infinite, and the number of naturals is also infinite. But the cardinality, okay, is actually bigger than set of natural numbers. So we name this C character here for continuum because set of reals is a continuum and is in fact strictly greater than Aleph null. It's a new level of infinity. Okay, so this is a huge result, and this shows that infinity is not one single level. Okay, you have an infinite, but infinity is not one single concept. You have infinitely many levels of infinity because real numbers is bigger than natural numbers and integers and rational numbers. But there are sets even bigger than real numbers that we will see. Okay, so this leads to the fact that there are infinitely many levels of infinites. Not all infinites are the same. And essentially, for the purposes of this course, what is distinctive about this is set of real numbers is not countably infinite. It is uncountable. Okay, so for our purposes for this course, being countable and being not being countable is essential. Okay, so there is a characteristic difference between the set of naturals, integers, rational numbers, etc., and the set of reals. And one final remark on this, Cantor's diagonal argument is quite important, and it also appears in, as a method, it also appears in Gödel's proof of incompleteness theory. So it's an extremely powerful tool, and it has been a standard tool in set theory in such proofs. And it was quite a contribution by Georg Cantor, as he is now seen as the father of modern set theory.